In mathematics, especially in order theory, a preorder or quasi-order is a binary relation that is reflexive and transitive. All equivalence relations and partial orders are preorders, but preorders are more general. The name preorder comes from the idea that preorders are almost orders, but not quite. They're neither necessarily antisymmetric nor symmetric. Because a preorder is a binary relation, the symbol can be used as the notational device for the relation. However, because they are not necessarily antisymmetric, some of the ordinary intuition associated to the symbol may not apply. On the other hand, a preorder can be used, in a straightforward fashion, to define a partial order and an equivalence relation. Doing so, however, is not always useful or worthwhile, depending on the problem domain being studied. In words, when a B, one may say that B covers A, or that A precedes B, or that B reduces to A. Occasionally, the notation OR is used instead of. To every preorder, there corresponds a directed graph, with elements of the set corresponding to vertices, and the order relation between pairs of elements corresponding to the directed edges between vertices. The converse is not true. Most directed graphs are neither reflexive nor transitive. In general, the corresponding graphs may contain cycles. A preorder that is antisymmetric no longer has cycles. It is a partial order, and corresponds to a directed acyclic graph. A preorder that is symmetric is an equivalence relation. It can be thought of as having lost the direction markers on the edges of the graph. In general, a preorder may have many disconnected components. Formal definition. Consider some set P in a binary relation on P. Then is a preorder, or quasi-order, if it is reflexive and transitive, i.e., for all A, B and C in P, we have that. Or if a B and B C then a CA set that is equipped with a preorder is called a preordered set. If a preorder is also antisymmetric, that is, a B and BA implies or equals B, then it is a partial order. On the other hand, if it is symmetric, that is, if a B implies BA, then it is an equivalence relation. Equivalently, the notion of a preordered set P can be formulated in a categorical framework as a thin category, i.e., as a category with at most one morphism from an object to another. Here the objects correspond to the elements of P, and there is one morphism for objects which are related, zero otherwise. Alternately, a preordered set can be understood as an enriched category, enriched over the category 2 equals. A preordered class is a class equipped with a preorder. Every set is a class, and so every preordered set is a preordered class. Examples. The reachability relationship in any directed graph gives rise to a preorder, where x, y in the preorder if and only if there is a path from x to y in the directed graph. Conversely, every preorder is the reachability relationship of a directed graph with x, y. However, many different graphs may have the same reachability preorder as each other. In the same way, reachability of directed acyclic graphs, directed graphs with no cycles, gives rise to partially ordered sets. Every finite topological space gives rise to a preorder on its points, in which x, y if and only if x belongs to every neighborhood of y, and every finite preorder can be formed as the specialization preorder of a topological space in this way. That is, there is a one-to-one correspondence between finite topologies and finite preorders. However, the relation between infinite topological spaces and their specialization preorders is not one-to-one. A net is a directed preorder, that is, each pair of elements has an upper bound. The definition of convergence via nets is important in topology, where preorders cannot be replaced by partially ordered sets without losing important features. The relation defined by f, where f is a function into some preorder. The relation defined by if there exists some injection from x to y. Injection may be replaced by surjection, or any type of structure or preserving function, such as ring homomorphism, or permutation. The embedding relation for countable total orderings. The graph minor relation in graph theory. A category with at most one morphism from any object to any other object is a preorder. Such categories are called thin. In this sense, categories generalize preorders by allowing more than one relation between objects. Each morphism is a distinct preorder relation. In computer science, one can find examples of the following preorders. Many one- and Turing reductions are preorders on complexity classes. The subtyping relations are usually preorders. Simulation preorders are preorders. Reduction relations in abstract rewriting systems. The encompassment preorder on the set of terms, defined by St if a subterm of T is a substitution instance of S. Example of a total preorder. Preference, according to common models. Uses. Preorders play a pivotal role in several situations. Every preorder can be given a topology, the Alexandrov topology, and indeed, every preorder on a set is in one-to-one correspondence with an Alexandrov topology on that set. Preorders may be used to define interior algebras. Preorders provide the Kripke semantics for certain types of modal logic constructions. Every binary relation R on a set S can be extended to a preorder on S by taking the transitive closure and reflexive closure, R plus equals. The transitive closure indicates path connection in R, X R plus Y if and only if there is an R path from X to Y. Given a preorder on S, one may define an equivalence relation tilde on S such that a tilde B if and only if A B and B A. Using this relation, it is possible to construct a partial order on the quotient set of the equivalence S tilde, the set of all equivalence classes of tilde. Note that if the preorder is R plus equals S tilde is the set of R cycle equivalence classes X, Y, if and only if X equals Y or X is in an R cycle with Y. In any case, on S tilde we can define X, Y, if and only if X, Y. By the construction of tilde, this definition is independent of the chosen representatives and the corresponding relation is indeed well defined. It is readily verified that this yields a partially ordered set. Conversely, from a partial order on a partition of a set S, one can construct a preorder on S. There is a one-to-one correspondence between preorders and pairs. For a preorder, a relation less than can be defined as a less than B if and only if, or equivalently, using the equivalence relation introduced above. It is a strict partial order. Every strict partial order can be the result of such a construction. If the preorder is antisymmetric, hence a partial order, the equivalence is equality. So the relation less than can also be defined as a less than B if and only if. Doing so would cause problems if the preorder was not antisymmetric, as the resulting relation less than would not be transitive. Conversely, we have a B if and only if a less than B or a tilde B. This is the reason for using the notation can be confusing for a preorder that is not antisymmetric. It may suggest that a B implies that a less than B or equals B. Note that with this construction multiple preorders can give the same relation, less than, so without more information, such as the equivalence relation, cannot be reconstructed from less than. Possible preorders include the following. Define a B as a less than B or equals B. This gives the partial order associated with the strict partial order, less than, through reflexive closure. In this case the equivalence is equality, so we don't need the notations in tilde. Define a B as not B less than a, which corresponds to defining a tilde B as neither a less than B nor B less than if these relations and tilde are in general not transitive. However, if the tilde is an equivalence, in that case, less than is a strict weak order. The resulting preorder is total, that is, a total preorder. Number of preorders. As explained above, there is a one-to-one correspondence between preorders and pairs. Thus the number of preorders is the sum of the number of partial orders on every partition. For example, for n equals 3, one partition of 3, giving one preorder, 3 partitions of 2 plus 1, giving 3 times 3 equals 9 preorders, one partition of 1 plus 1, giving 19 preorders, i.e., together 29 preorders. For n equals 4, one partition of 4, giving one preorder, 7 partitions with 2 classes, giving 7 times 3 equals 21 preorders, 6 partitions of 2 plus 1, giving 6 times 19 equals 114 preorders, one partition of 1 plus 1, giving 219 preorders, i.e., together 355 preorders. Interval. For AB, the interval AB is the set of points x satisfying AX and XB, also written AXB. It contains at least the points A and B. One may choose to extend the definition to all pairs. The extra intervals are all empty. Using the corresponding strict relation, less than, one can also define the interval as the set of points x satisfying A less than x and x less than b, also written A less than x less than b. An open interval may be empty even if A less than b. Also, A, B, and A, B can be defined similarly.